Okay, here's a couple of examples, and these guys are right in the book too, page 167, example 2 and 3. So we'll do these together, and then I'll give you some problems to try for tomorrow. All right, so what we're trying to do is find extremes. To find extremes, we're going to use the tangent line. We either have a horizontal tangent line, or we have a point where the tangent line does not exist. So we got to try to figure out where those possibilities are. And those are called critical values. Now, just because you find critical values doesn't mean you're going to have a max or min. You might have a flat spot or something else going on. But you'll be given a function, and in this case, there's an interval. So we're only looking on the x-axis between -1 and 2. Now, you can do a lot of pre-calc stuff to graph these. I mean, just get a picture on your calculator too, but if you factor this guy, take out the x cubed, you end up with this. So this gives you x equals 0, and this gives you x equals 4/3. So those are the two possible points where you have zeros. The original is x to the 4th, so the end behavior is like a parabola. This is positive, so it's like a positive parabola. Triple root, so the function goes through the root. This is to the first power, so the multiplicities are odd, so they both go through at those points. Now this is x to the 3rd, this is the triple root, so you have a flat spot right there, a little inflection. And now it might not get perfectly horizontal, but most likely. Okay, so you look at this graph, we're only going from here, here's -1 to 2, and 2 is just beyond the 4/3 here. Alright, so that's what the graph looks like. Now you can see that right here looks like at x equals 1. It doesn't have to be. There's a relative min. There's the absolute max. And that's neither. That's just a flat spot. It's not a local max or min. And we should be able to see that by using the derivative. So you take the function's derivative, and then you want to find critical values by setting it equal to 0 and then setting it and finding where it's undefined. Now in this case, this thing will never be undefined, so we don't have to do this part. So I take the derivative, set it equal to 0. Where it's equal to 0, I'll get horizontal tangent lines. Okay, so it looks like here and here I should get critical values. So take this, factor, set each factor equal to 0, and look, I get x equals 0, x equals 1. Right, so those are the critical values. Now I have to determine what's happening at those points. So I'm going to make what is known as the first derivative table. So you take your interval, in this case -1 to 2, and you break it into sections based upon the critical values and the endpoints. So there's the 2 endpoints. Here's my critical values. So I put all these x coordinates in order on the number line. So -1, then 0, then 1, then 2. So before I make my table, I figure out how many columns I'm going to need to break up the number line. So we're going from -1 out here to 2. So we're just looking at that much of the x-axis. And then you just make the intervals in between. So this is looking at -1 to 0, 0 to 1, and then 1 to 2. And notice they're open. They're not including the endpoints. Okay. Now, these guys are the only possible places where I can have a horizontal tangent line. So now I'm going to use the derivative to see what's happening at the function or on the function at these points. Okay. Now I know that this is an endpoint, so I don't know about the derivative because I don't know what's happening after here. So I'm just going to leave this blank. But at 0, I know the value of the derivative is 0 because that's how I found it. So the value of the derivative is 0. The value of the derivative at 1 is also 0. Now I'm going to figure out what the function is doing in between these 2 points. What's it doing on this interval? Since these are the only times where the function could reach a max or a min, what the function is doing in between, increasing or decreasing, will always be the same. Like from -1 to 0, notice this function is totally decreasing. It can't change directions because there's no max or min in here. Right, so I can just check any point I want and see what the derivative is doing. So let's see, between -1 and 0, I don't know, I'll pick -0.5. And I'll see what's happening. Now when I plug in -0.5 into derivative, I'll end up getting a negative number. And you check it on your calculator. And all I'm going to do is write negative. That's all I care about. The derivative is negative. Because if the derivative is negative, that means the slopes of the tangent lines are negative. And lines with negative slope are decreasing. All the tangent lines in through here are decreasing. So what I know about the function on this interval just from -1 to 0 is that the function is decreasing. Now at 0, if I plug 0 into the function, I'll get 0. So that's the value of the function there. But I'm going to just leave filling in this row till after I've done this entire row. All right, so now if I plug -1 into the derivative, I'll get a value, but I really don't care what it is. All right, so now I'll go here and I'll plug in a number like 0.5 into there, into the derivative, and see what I get. So I take out my calculator, whatever, and I end up getting a negative value. So if the derivative is negative, the tangent lines have negative slope, so the function must be decreasing. The tangent lines are going that way. So again, the function's still decreasing. So notice, function decreasing, hits 0, and continues to decrease. So this is not a min or a max, because it just continues on its downward trend through that point. Pick a number between 1 and 2. There's 1 and there's 2. Notice like right here, all of this, the function's increasing, but if I take a number like 1.5 and plug it into the derivative, I'll get a positive value. So if the tangent lines are positive, the function must be increasing. Okay. And if I plug 1 into the function, 1, 3 minus 4, I'll get -1. Now if I take -1, plug it into the function, I get 7. I know that from up there. If I plug 2 into the function, I'll get 16. Okay. So we use the derivative to determine increasing versus decreasing. Now just look at this behavior and describe what's happening at the critical values. All right, so we start at 7, we decrease down to 0, and we continue to decrease. So this is not a relative max or min. Right. Decrease some more, get to -1, and then increase. So the function's going down, flattens out, and then starts to go back up again. So this guy right here is a relative min. At x equals -1, we have a relative min. Okay. Now if I look at all these y coordinates, these points are the only candidates for absolute max and min. So of these, there's the biggest y coordinate. So that guy's the absolute max. And let's see, the smallest y coordinate is right there. So not only is this a relative min, but it's an absolute min. Wow, 11 minutes. Whew.